What if every law of physics you have ever learned is not a description of nature, but a line of code? What if the stars overhead, the ground beneath your feet, and the very thoughts forming in your mind right now are computations running inside a system far older and far stranger than anything humanity has built? This is not science fiction. It is a hypothesis that has moved, in the last 2 decades, from the margins of philosophy into the working notebooks of theoretical physicists, computer scientists, and cosmologists at major research institutions around the world. The simulation hypothesis proposes that the universe we inhabit may not be a physical reality at all, but an enormously sophisticated computational construct. And within that hypothesis lives a darker, more provocative branch known as the glitch hypothesis, the idea that if our reality is indeed a simulation, then like every piece of software ever written, it must contain errors, imperfections, inconsistencies that occasionally surface in ways we cannot easily explain. Over the next several hours, this investigation will examine the scientific evidence, the mathematical reasoning, and the philosophical implications behind one of the most disorienting questions ever asked. We will look at the discrete structure of space-time at the Planck scale. We will examine quantum behavior that resembles rendering optimization. We will study reported anomalies, statistical oddities, and the strange fine-tuning of physical constants. And we will ask with the calm precision of a scientific investigation rather than the heat of speculation, whether the universe behaves more like a closed natural system or like a program with bugs. The question is no longer whether the hypothesis can be entertained. Serious researchers are entertaining it. The question is what the evidence examined honestly actually suggests. The first cracks in our confidence about the nature of reality did not appear in laboratories or observatories. They appeared in equations. For most of human history, the physical world seemed obviously and inarguably solid. Stones were stones, water was water. The sky was a vast and indifferent canopy stretched over a tangible earth. Whatever questions philosophers posed about appearance and reality, the working assumption of every farmer, builder, sailor, and soldier was that the world they touched was the world that existed. Reality was what could be weighed, measured, and broken. Anything else was speculation. That confidence began to erode in the early 20th century, and the erosion has not stopped since. When physicists peered into the atom, they did not find smaller versions of the world they already knew. They found something stranger. Particles that behaved like waves, waves that behaved like particles, objects that seemed to exist in multiple places at once until they were observed, at which point they settled into a single location, as if reluctantly committing to a position. The deeper science looked, the less the universe resembled a collection of solid things, and the more it resembled a network of relationships, probabilities, and information. Matter, examined closely enough, dissolved into something that behaved less like substance and more like data. This shift was unsettling, but it remained safely confined to the strange world of the very small. Most physicists assumed that the weirdness of quantum mechanics would eventually be reconciled with the familiar physics of ordinary objects, and that some deeper layer of reality would restore the solidity that classical thinking had taken for granted. That reconciliation never arrived. Instead, as instruments improved and theories became more refined, the quantum strangeness was confirmed again and again, with increasing precision and across increasingly large systems. Whatever the universe is made of, it is not made of the kind of matter that our intuition expects. At the same time, an entirely different field was undergoing its own revolution. Beginning in the middle of the 20th century, computer scientists began to explore the limits of computation. They asked what could and could not be calculated, what kinds of systems could simulate other systems, and how much information was required to represent a given physical process. Out of this work came a startling realization. Almost any physical system, no matter how complex, could in principle be simulated by a sufficiently powerful computer, provided the simulation had enough memory and enough processing time. There was no fundamental barrier between physics and computation. The two were, at a deep level, expressions of the same underlying logic. By the late 20th century, these two streams began to converge. Physicists studying black holes discovered that the amount of information a region of space could contain was not unlimited. It was bounded, and the bound was related to surface area rather than volume, a result so counterintuitive it took years to digest. Computer scientists studying virtual environments built increasingly convincing simulations of physical processes, from weather systems to evolutionary dynamics to the folding of proteins. Game designers with vastly less computing power than research laboratories produced worlds that millions of people experienced as immersive and emotionally real, despite knowing those worlds were constructed from polygons and shaders. The line between physical reality and computed reality, which once seemed obvious, began to blur. It was against this backdrop that a small number of philosophers and scientists began to ask a question that earlier generations would have dismissed as absurd. If a sufficiently advanced civilization could simulate a universe, and if such a civilization would have reasons to do so, then how confident could we be that we ourselves are not living inside such a simulation right now? The question is not new in its broadest form. Variations of it appear in ancient Hindu philosophy, in Plato's allegory of the cave, in the writings of Descartes, who famously wondered whether an evil demon might be deceiving him about the nature of the world. What is new is the technological context. For the first time in human history, we are building simulated worlds ourselves, and we can begin to ask in concrete and quantitative terms what it would take to build one indistinguishable from our own. The cracks in reality, then, are not necessarily literal cracks. They are the gaps between what we expect the universe to be and what it actually behaves like under careful examination. The expectation, inherited from millennia of practical experience, is that the world is continuous, smooth, and independent of observation. The reality, as revealed by experiment after experiment, is that the world is granular at small scales, behaves differently when measured than when unmeasured, and is governed by mathematical relationships of astonishing precision and economy. None of this proves that we live in a simulation, but all of it raises a question that cannot be dismissed without careful argument. Why does the universe behave so much like a computation? Consider the structure of physical law itself. The laws of physics, as they have been discovered over the past 4 centuries, are remarkable for their simplicity and their universality. The same equations that describe the orbit of a planet describe the trajectory of a thrown stone. The same principles that govern the behavior of light describe the operation of a microwave oven and the function of the eye. There is no obvious reason why the universe should be like this. A reality that emerged from random origins might be expected to be messy, inconsistent, governed by different rules in different places, full of exceptions and special cases. Instead, the universe appears to be governed by a small set of mathematical principles that apply with extraordinary uniformity across the entire observable cosmos. This uniformity is so striking that the physicist Eugene Wigner, in a famous essay, called it the unreasonable effectiveness of mathematics. He could not explain why mathematics, an abstract human invention, should describe physical reality so precisely. He could only marvel at the fact that it does. A simulation hypothesis offers a possible explanation. If the universe is a computation, then the laws of physics are simply the rules of the program. They are uniform across the cosmos because the same code is running everywhere. They are mathematically elegant because mathematical elegance is also computational efficiency. A simulation written in the simplest possible language would be the easiest to run, the easiest to debug, and the most stable over long periods of operation. The unreasonable effectiveness of mathematics on this view is not unreasonable at all. It is exactly what you would expect if the substrate of reality were code. This is, of course, only one possible explanation. There are others, and they are debated vigorously. The mathematical universe hypothesis, proposed by the cosmologist Max Tegmark, suggests that mathematical structures themselves are the ultimate reality, and that physical existence is simply what mathematical structures feel like from the inside. Other physicists argue that the apparent simplicity of physical law is an artifact of human cognition, a consequence of our brains being designed to find patterns. Still others maintain that the universe is fundamentally physical and that any computational analogies are just that, analogies useful for human understanding but not reflective of what the cosmos actually is. The debate is far from settled. What has changed, and what makes the present moment unusual in the history of thought, is that the simulation hypothesis is no longer dismissed out of hand by serious thinkers. Physicists at major universities have published papers exploring how it might be tested. Philosophers have constructed careful arguments about its probability. Computer scientists have analyzed the resource requirements of running such a simulation and have concluded that, while enormous, they are not necessarily beyond the reach of a sufficiently advanced civilization. The hypothesis has graduated from a dorm room thought experiment to a topic of legitimate, if speculative, academic inquiry. And as it has done so, attention has begun to focus on a particular question that has profound consequences if the hypothesis is even partially correct. If the universe is a simulation, is it perfect? And if not, what would its imperfections look like? It is here, in the search for cracks within the cracks, that the investigation begins to take on its most peculiar and most consequential form. To understand why the simulation hypothesis cannot be casually dismissed, it helps to follow the precise reasoning that brought it into mainstream academic discussion. The argument that did this, more than any other, was published in 2003 by the Swedish philosopher Nick Bostrom, then at Oxford University. His paper, titled simply "Are You Living in a Computer Simulation?", did not claim to prove that we are. It made a far subtler and far more disturbing claim. It claimed that, given a small number of reasonable assumptions, at least one of 3 propositions must be true, and that 2 of them have consequences nearly as strange as the third. The argument has come to be known as the simulation trilemma, and it has resisted serious refutation for more than 2 decades. Bostrom began with an observation about the trajectory of computing power. Throughout the second half of the 20th century, the number of operations a computer could perform per second doubled roughly every 2 years, a pattern known as Moore's Law. The same trend held for memory capacity, storage density, and the resolution of digital displays. While there are physical limits to how far this trend can continue using current silicon-based technology, there is no theoretical reason why computation cannot continue to advance through other means, including quantum computing, optical computing, and architectures we have not yet imagined. Bostrom asked a simple question. If this trend continues for centuries or for thousands of years, what would be possible? His answer, supported by careful calculation, was that a civilization at a sufficiently advanced stage of technological development would be able to harness the resources of an entire planet or even an entire star system to run computations of staggering complexity. Such a civilization, which Bostrom called a post-human civilization, might be able to simulate the entire history of human consciousness with all its detail and all its experiences using only a tiny fraction of its available computing power. A single post-human computer, dedicated to historical simulation, might run countless instances of human civilization simultaneously. From this starting point, Bostrom constructed his argument. If post-human civilizations exist, and if even a small fraction of them are interested in running ancestor simulations, simulations of their own evolutionary past, or of the development of consciousness more generally, then the number of simulated minds in the universe would vastly outnumber the number of biological minds, by a vast margin. For every original biological human who ever lived, there might be billions or trillions of simulated humans living through historical scenarios. And here the argument turns. If you are a randomly selected mind in the universe, and if simulated minds outnumber biological minds by such an extreme ratio, then the probability that you yourself are biological is vanishingly small. By simple statistical reasoning, you are almost certainly inside one of those simulations. This conclusion is so unsettling that most people instinctively look for a way to escape it. Bostrom anticipated this. He framed his argument as a trilemma, presenting three possibilities and arguing that at least one of them must be true. The first possibility is that the human species, or any species like ours, almost always goes extinct before reaching the post-human stage. Civilizations capable of running ancestor simulations, on this view, simply do not exist, because all civilizations destroy themselves through war, environmental collapse, or technological catastrophe before they reach that level of capability. The second possibility is that post-human civilizations do exist, but that virtually none of them are interested in running ancestor simulations. Perhaps such simulations are considered ethically problematic. Perhaps they are simply boring to advanced minds. Perhaps the resources required, while available, are better spent on other pursuits. The third possibility is that we are almost certainly living in a simulation right now. The structure of the argument is what makes it so difficult to dismiss. To reject the conclusion, one must commit to one of the first two possibilities, but each of those possibilities has its own troubling implications. To accept the first is to accept that civilizations like ours are doomed, that there is some filter, some barrier that prevents technological species from advancing beyond a certain point. This view has its own name in academic circles, the Great Filter Hypothesis, and it is taken seriously by researchers studying the absence of detectable extraterrestrial civilizations. To accept the second is to accept that whatever advanced civilizations exist have collectively chosen, with near unanimity, to abstain from a particular kind of computational activity. This is conceivable, but it requires assuming a uniformity of values across all possible advanced civilizations that is not obviously plausible. To accept the third is to accept that the world around us is not what it appears to be. There is no comfortable option. Each branch of the trilemma is, in its own way, profoundly strange, and the argument does not depend on any exotic assumptions. It does not require accepting any particular metaphysics. It does not require believing in any specific technology beyond the reasonable extrapolation of trends already underway. It requires only that consciousness can in principle be simulated, that some advanced civilizations would want to run such simulations, and that statistical reasoning applies to one's own existence. From these modest premises, the argument generates a conclusion that has unsettled philosophers, physicists, and computer scientists ever since. The first premise, that consciousness can be simulated, is the one most often challenged. Some philosophers argue that subjective experience cannot arise from computation, no matter how sophisticated, because there is something fundamentally non-computational about consciousness itself. This is the view associated with thinkers like John Searle, whose famous Chinese room argument suggests that a system can perform all the functions of understanding without actually understanding anything. Other philosophers, particularly those working in the tradition of functionalism, take the opposite view. They argue that consciousness is whatever process produces certain functional behaviors, and that any system performing those functions, regardless of its physical substrate, would be conscious. The debate is unresolved and may remain so. But Bostrom's argument does not require taking a definitive position. It requires only that the functionalist view be possibly correct. As long as there is some chance that consciousness can arise in computation, the trilemma applies, with the probability of the third branch being scaled by the probability of the functionalist view. The second premise, that some advanced civilizations would want to run ancestor simulations, also invites scrutiny. We can examine our own civilization for clues. Already in the early 21st century, with technology vastly less powerful than what post-human civilizations would possess, humans run simulations of historical battles, simulations of evolutionary processes, simulations of weather systems centuries old, and simulations of consciousness in the form of video games and virtual reality. The motivations are varied, including scientific research, education, entertainment, and aesthetic pleasure. There is no reason to assume these motivations would disappear in a more advanced society. If anything, the diversity of motivations would likely expand. And among the vast number of advanced civilizations that might exist across the cosmos, It seems plausible that at least some would dedicate substantial resources to running detailed simulations of their evolutionary past. To assume otherwise is to assume a remarkable uniformity of preferences among all possible minds. The third premise, the application of statistical reasoning to one's own existence, is the most subtle. It rests on what philosophers call the self-sampling assumption, the idea that you should reason about your own location in the universe as if you were a randomly selected observer from among all observers like yourself. This kind of reasoning is used routinely in cosmology, where it is sometimes called the anthropic principle. It is not without controversy, but it is not arbitrary either. It is grounded in basic probability theory. If most observers like you are simulated, then you are probably simulated. The reasoning is the same that would lead you to conclude, upon waking up in a hospital ward of 100 patients, that you are probably one of the 99 other patients rather than the one patient with a rare condition. Bostrom himself was careful not to claim that his argument proved we are in a simulation. He claimed only that one of the three propositions must be true, and that there is no obvious way to determine which. His own estimate, expressed in interviews and follow-up papers, has fluctuated, but he has consistently maintained that the simulation possibility deserves serious consideration. Other philosophers and scientists have engaged with the argument extensively. Some have proposed refinements, some have proposed counter-arguments. None have produced a refutation that has gained widespread acceptance. The trilemma stands, and its consequences extend far beyond the academic world. If we cannot rule out that we are in a simulation, then a series of further questions become unavoidable. What kind of simulation might it be? What are its rules? And, perhaps most pressingly, are there any signs that those rules are being implemented imperfectly? If the universe is a computation, then somewhere in its structure there should be evidence of its computational nature. A simulation, no matter how sophisticated, must use finite resources. It must represent space, time, energy, and matter in some discrete form, because no physical computer, regardless of its scale, can manipulate truly continuous quantities. Continuous values have infinite precision, and infinite precision requires infinite memory. A simulation that ran on infinite memory would not be a simulation at all. It would be a contradiction in terms. So if our universe is being computed, then beneath the apparent smoothness of space and time, there should be a grain, a pixel, a smallest unit beyond which finer detail does not exist. And remarkably, when physicists examine the universe at sufficiently small scales, that is exactly what they appear to find. The unit in question is called the Planck length, named after the German physicist Max Planck, who first identified it in 1899 as part of a system of natural units derived from fundamental physical constants. The Planck length is approximately 1.6 times 10 to the negative 35th meter. To put that in perspective, if an atom were enlarged to the size of the observable universe, the Planck length within that atom would be smaller than a grain of sand. It is the smallest meaningful distance in physics, the scale at which the very concepts of space and distance begin to break down. Below the Planck length, current physics has nothing to say. The equations of quantum mechanics and general relativity, which describe the universe accurately at every scale we've probed, simply stop functioning. They produce nonsensical answers, infinities, and contradictions that suggest something fundamental about the nature of space changes at this scale. Most physicists interpret this breakdown as a sign that we lack a complete theory of quantum gravity, a unified framework that would replace both general relativity and quantum mechanics with a deeper description. The hope is that such a theory, when it is finally developed, will smoothly extend our understanding into the sub-Planckian regime, revealing whatever happens at those scales. But there is another interpretation, one that becomes increasingly difficult to ignore as the simulation hypothesis is taken more seriously. The Planck length may not be a limit of our current theories. It may be a limit of reality itself. It may be the resolution of the universe, the smallest unit of space that the cosmos actually represents. Beneath it, there is nothing to find, because there is nothing there. The universe simply does not store finer detail. A parallel observation applies to time, as The Planck time, derived from the Planck length divided by the speed of light, is approximately 5.4 times 10 to the negative 44th seconds. It is the smallest meaningful interval of time in current physics, the duration during which light, the fastest entity in the universe, can traverse exactly one Planck length. Below this interval, time becomes as ill-defined as space at sub-Planckian scales. Events that take less time than this cannot be distinguished from one another. There is no observation, no measurement that could detect a duration shorter than the Planck time, not because our instruments are inadequate, but because the universe itself does not appear to keep finer track. Time, like space, seems to advance in discrete steps rather than flowing continuously. This discreteness is precisely what one would expect from a computational substrate. Every digital simulation operates in discrete units. The screen of a computer is composed of pixels, each one a discrete unit of color. The audio of a digital recording is composed of samples, each one a discrete unit of sound. The simulation of a physical system on a computer proceeds in discrete time steps, each one updating the state of the system before moving to the next. There is no continuous motion in any computer simulation. There is only a sequence of static states, presented quickly enough that the transitions appear smooth to an observer. If the universe is a simulation, then space and time should likewise be quantized at some fundamental level, and they appear to be. The Planck scale may be the resolution at which the universe is rendered. This interpretation is not the consensus view among physicists. It is one possibility among several, and it has not been proven, but it is taken seriously, and the evidence in its favor is more than circumstantial. Consider the strange fact that the Planck length, derived purely from fundamental constants, the speed of light, the gravitational constant, and Planck's reduced constant, has no obvious connection to any human or biological scale. It emerges from the mathematics of physics itself, with no input from human experience, and yet it appears to mark a genuine threshold in the structure of reality. This is not the behavior we would expect from an arbitrary mathematical construct. It is the behavior we would expect from a fundamental property of the universe, a property baked into its underlying architecture. There are theoretical frameworks in modern physics that explicitly treat space and time as discrete. Loop quantum gravity, one of the leading candidates for a theory of quantum gravity, proposes that space is composed of indivisible units called spin networks. These networks are not embedded in a continuous space. They are space itself, woven from discrete relationships between quantum states. According to this theory, the apparent smoothness of space at large scales emerges from the statistical behavior of vast numbers of discrete units, just as the apparent smoothness of a beach emerges from the collective behavior of countless individual grains of sand. Loop quantum gravity makes specific predictions about how this discreteness should manifest at the Planck scale, including the prediction that certain physical quantities, like area and volume, should come in discrete amounts rather than taking any continuous value. Some experimental tests of these predictions are being developed, though direct measurement at the Planck scale remains far beyond current technology. Another framework, causal set theory, takes the discreteness of space-time as its foundational principle. In this view, the universe is composed of a vast collection of fundamental events, each one related to other events by relationships of causality. There is no continuous space-time in causal set theory. There are only discrete events and the causal connections between them. The apparent geometry of space and time emerges from the statistical structure of these connections. This framework, developed by physicists like Raphael Sorkin, has produced some intriguing results, including a prediction about the value of the cosmological constant that turned out to be an approximate agreement with observation. It is far from a complete theory, but it represents a serious scientific attempt to take the granular nature of space-time as a starting point. These theories were not developed with the simulation hypothesis in mind. They were developed by physicists trying to solve the problem of quantum gravity, a problem that has resisted solution for nearly a century. But the fact that the most promising candidate theories all involve some form of fundamental discreteness is suggestive. It is consistent with what we would expect if reality were a computation, even though that is not what their authors set out to demonstrate. The convergence of physics on a discrete picture of spacetime from multiple independent theoretical directions gives the simulation hypothesis a kind of indirect support that it would not otherwise have. There are also more direct lines of evidence, or at least suggestive observations, that hint at the discrete nature of reality. The maximum energy of cosmic rays, the highest energy particles ever detected, appears to be bounded by a quantity related to the Planck scale. Some interpretations of certain quantum experiments suggest that information itself comes in discrete units, as if the universe were keeping track of its contents using a fundamental currency of bits. The black hole entropy formula, derived by Stephen Hawking and others, relates the information content of a black hole to its surface area in units of the Planck length squared, suggesting that information is stored on the boundaries of regions of space at exactly the resolution we would expect from a discrete underlying structure. What does all this mean? Taken individually, none of these observations proves that the universe is a simulation. They are all consistent with various other theoretical interpretations. But taken together, they paint a picture of a universe that does not behave like the smooth, continuous, infinitely divisible cosmos imagined by classical physics. They paint a picture of a universe that is, at its deepest level, granular, pixelated, composed of discrete units with a fundamental resolution beyond which finer detail does not exist. Whether this discreteness reflects the computational nature of reality, the limits of our theoretical frameworks, or some deeper truth that we have not yet grasped, is a question that current science cannot definitively answer. But the question is being asked, and the more we learn about the structure of spacetime at small scales, the more the discrete picture appears to be the correct one. If you look closely enough at the universe, the smooth fabric of reality does not get smoother. It breaks into pieces, and those pieces, those tiny units of existence, behave in ways that are difficult to reconcile with anything other than a computational substrate. The universe, on its smallest scale, looks like a screen viewed through a magnifying glass, and screens, no matter how detailed, are always built from pixels. The discreteness of spacetime is only one piece of the puzzle. The deeper one looks into the behavior of matter itself. The more the universe begins to resemble not just a computation, but a computation that has been carefully optimized. Nowhere is this more apparent than in the strange domain of quantum mechanics, where particles do not appear to occupy definite states until they are measured, where information seems to be processed in ways that defy classical logic, and where the act of observation itself plays a role unlike anything in our everyday experience. If the universe is software, then quantum mechanics may be the place where its rendering engine reveals itself most clearly. The phenomenon at the heart of this strangeness is called quantum superposition. According to the standard interpretation of quantum mechanics, any particle that has not been measured exists not in a single definite state, but in a combination of all possible states simultaneously. An electron orbiting an atom does not occupy a particular position until something interacts with it. Before that interaction, the electron is described by a mathematical object called a wave function, which assigns probabilities to every possible position the electron could be found in. The wave function is not a description of our ignorance about where the electron is. It is, according to most physicists, a description of where the electron actually is. The electron is everywhere it could be, all at once, until measurement forces it to commit to a single location. Only at that moment does the wave function collapse and the electron acquires a definite position. This behavior is so counterintuitive that for nearly a century, physicists have debated what it actually means. Some argue that the wave function is a real physical entity and that particles genuinely exist in multiple states until measured. Others argue that the wave function is a mathematical tool, a way of calculating probabilities, and that the underlying reality is something we cannot directly access. Still others argue that there is no collapse at all, and that every possible outcome of every quantum measurement actually occurs in a different branch of a continuously splitting universe. None of these interpretations has emerged as clearly correct, and the debate continues. What is not debated is the experimental reality. Particles do behave as if they exist in superposition. The mathematics works. The predictions are confirmed to extraordinary precision. Whatever quantum mechanics is describing, it is describing it accurately. From the perspective of the simulation hypothesis, quantum superposition takes on a fascinating new significance. It looks remarkably like a form of computational optimization. In any large simulation, one of the central challenges is managing limited resources. A simulated environment cannot calculate every detail of every part of itself at every moment. To do so would require resources that scale with the size of the simulation in ways that quickly become impractical. Real video games, for example, do not render every leaf on every tree in every part of their world all the time. They render only what the player can see, and only at the level of detail required for the current view. Objects far from the player are represented with simplified models. Objects behind the player are not rendered at all. Only when the player turns to look at them do they come into full existence as detailed graphical objects. This technique, known as level of detail rendering or view frustum culling, is essential to making large simulations feasible on finite hardware. Quantum superposition resembles this kind of optimization with uncomfortable precision. A particle that is not being observed does not need to have a definite state, because nothing in the simulation depends on its specific properties at that moment. The simulation can save resources by representing the particle only in terms of probabilities, the range of possible states it might be in. Only when something actually interacts with the particle, when a measurement is made, does the simulation need to commit to a specific value. At that moment, the wave function collapses and the particle acquires definite properties. This interpretation does not require the universe to be a simulation. The mathematics of quantum mechanics is the same regardless of how it is interpreted. But the structural similarity to computational optimization is striking enough that several physicists have remarked on it, and at least a few have suggested that it should be taken as a serious clue rather than a coincidence. The most famous experiment that demonstrates this behavior is the double-slit experiment, performed in various forms since the early 19th century, but refined over the 20th century into one of the most carefully studied phenomena in physics. The experiment is simple in concept. A source emits particles, electrons, photons, or even larger objects toward a barrier with two slits in it. Beyond the barrier, a detector records where the particles arrive. When the experiment is performed without trying to determine which slit each particle goes through, the pattern on the detector shows interference fringes, the kind of pattern produced when waves passing through both slits combine and overlap. This is true even when particles are sent through the slits one at a time. Each individual particle somehow seems to pass through both slits and interfere with itself. But when an additional measurement is added, an instrument that detects which slit each particle actually goes through, the interference pattern disappears. Particles begin to behave like ordinary objects, going through one slit or the other and producing two simple bands on the detector instead of the interference pattern. The mere act of measuring which slit the particle went through changes the outcome. The particle, when observed, behaves like a particle. When not observed, it behaves like a wave that occupies multiple paths simultaneously. This experiment has been performed countless times with increasingly sophisticated equipment, and the results have always been the same. It is one of the most reliably reproducible phenomena in physics. And it raises a question that has no comfortable answer in classical terms. How does the particle know whether it is being observed? How does its behavior change based on whether or not a measurement is being made, even when the measuring instrument is far from the path the particle takes? The standard answer, that the wave function describes possibilities rather than realities, is mathematically sound, but conceptually unsatisfying. It tells us how to calculate the outcomes, but not what is actually happening at the level of physical reality. If the universe is a simulation, then the answer becomes simpler. Perhaps disturbingly so. The particle does not have a definite path because the simulation has not bothered to compute one. Until something requires the particle to have a specific position, the simulation tracks only the probability distribution of where it might be, which is computationally cheaper than tracking a specific trajectory. When a measurement is made, the simulation must produce a definite answer, and so it does, sampling from the probability distribution and committing to a specific outcome. The interference pattern arises because, when no measurement is made, the simulation is free to compute the behavior of the wave function in its full mathematical generality, allowing it to interfere with itself across multiple paths. When a measurement is made, the simulation must collapse the wave function to a single value, eliminating the interference. This interpretation is not provable, and it is not universally accepted, but it is consistent with the experimental evidence, and it offers a kind of conceptual clarity that other interpretations lack. It also makes a prediction. If quantum superposition is a form of computational optimization, then it should be possible to detect signs of the optimization in other ways. We should expect to find that the universe behaves as if it is conserving computational resources, rendering only what is necessary, and committing to specific values only when forced to do so by interaction with other systems. And in fact, this is exactly what we observe. Across many domains of physics, the universe appears to operate according to principles of efficiency and economy that are remarkable for their consistency. There is another aspect of quantum behavior that resembles computational optimization, called quantum entanglement. When two particles become entangled, they share a quantum state that cannot be described in terms of the individual particles alone. A measurement performed on one particle instantly affects the state of the other, regardless of how far apart they are. This phenomenon, which Einstein famously called spooky action at a distance, has been experimentally verified to extraordinary precision. The information about the state of one particle does not have to travel to the other in any conventional sense. The two particles simply share a state, and that shared state is updated instantly when either particle is measured. From a classical perspective, entanglement is deeply puzzling. It seems to violate the principle that information cannot travel faster than light. Strict analysis shows that no usable information is actually transmitted, but the correlations between entangled particles are real and are tighter than anything classical physics permits. From a computational perspective, however, entanglement is exactly what one would expect if the universe were tracking related particles with shared variables. In a database, two records that share a common field can be updated simultaneously by changing the value in one place. The records do not need to communicate with each other. The shared field is a single piece of data, accessible from multiple locations. Quantum entanglement behaves remarkably like this kind of shared data structure. The two particles are not separate entities exchanging information. They are pointers to the same underlying state. These analogies are not proofs. They are observations about the structural similarity between quantum behavior and computational design. But the similarities are persistent and detailed. Across multiple aspects of quantum mechanics, the universe behaves in ways that resemble the optimizations a programmer would use to make a simulation more efficient. Whether this resemblance is coincidental, whether it reflects a deeper truth about the computational nature of reality, or whether it simply reveals the limits of our intuitions about what physical reality should look like, remains an open question. But the question is being asked with increasing seriousness, and the answers, when they come, may reshape our understanding of what the universe actually is. Among the most fundamental constants of nature, the speed of light occupies a peculiar position. It is the maximum velocity at which any signal, any particle, any influence whatsoever can propagate through space. Approximately 300 million meters per second, this limit applies universally and absolutely. No experiment has ever found an exception. No theoretical framework that respects relativity allows for one. The speed of light is, in every observable sense, a hard ceiling on the rate at which the universe permits anything to happen. Why this particular value, and why such a strict limit at all, is one of the deepest unanswered questions in physics. And from the perspective of the simulation hypothesis, it is one of the most suggestive. Consider what a maximum speed actually does. It establishes a fundamental relationship between space and time. It dictates that no event in one region of the universe can affect any event in another region faster than light could travel between them. It means that the universe has a built-in latency, a minimum delay between cause and effect that depends on distance. If something happens on the surface of the sun, it cannot affect anything on Earth for at least 8 minutes, because that is how long light takes to make the journey. There is nothing in the laws of physics that requires this. We can imagine a universe with no speed limit, where influences propagate instantaneously across any distance. Such a universe would be perfectly logical. It simply is not the universe we inhabit. The speed of light is more than just a maximum velocity. It is the conversion factor between space and time in the equations of relativity. It is the speed at which all massless particles, including light itself and the carriers of certain fundamental forces, must always travel. It is the speed at which information itself propagates through any medium that respects the structure of space-time. The universe is not built around the speed of light as a special case. The speed of light is built into the universe at its most basic level. From a computational perspective, a maximum speed has a very natural interpretation. It is the rate at which the simulation updates its state. In any digital simulation, no matter how sophisticated, there's a fundamental limit to how fast information can propagate from one part of the simulation to another. This limit is set by the processing speed of the underlying hardware, by the architecture of the memory system, and by the way the simulation is structured to handle parallel updates. A simulation cannot allow influences to travel infinitely fast, because that would require infinite computing power. There must be a limit, and that limit is what we would experience from inside the simulation as a maximum velocity for the propagation of physical effects. In a simulated universe, the speed of light might be a direct reflection of the clock speed of the underlying processor. Each tick of the simulation clock allows information to propagate by a fixed amount, the Planck length, in a fixed time, the Planck time. The ratio of these two quantities, naturally, equals the speed of light. This is not a coincidence. It is a consequence of the same fundamental architecture. The speed of light on this view is not a property of light. It is a property of the simulation. Light just happens to travel at the maximum speed because, having no mass, there is nothing to slow it down. Other massless particles do the same, traveling at exactly the same speed, because the speed is set by the simulation itself, rather than by any property of the particles. This interpretation also explains why the speed of light is the same for all observers, regardless of their motion. In classical physics, this is one of the most counterintuitive aspects of relativity. If you are running toward a light source, you might expect the light to be moving faster relative to you than it would be if you were standing still. But this is not what happens. The speed of light is the same in every frame of reference, no matter how the observer is moving. Special relativity makes this fact mathematically precise, but it does not explain why the universe should behave this way. From a computational perspective, the explanation is straightforward. The simulation updates at a fixed rate, and influences propagate at a fixed speed relative to the simulation itself. The motion of any individual observer cannot change the underlying clock speed of the simulation, and so the speed of light appears the same to every observer. There is another aspect of the speed of light that fits the computational picture. The closer a massive object approaches the speed of light, the more energy is required to accelerate it further. Approaching the speed of light requires increasing amounts of energy, and reaching the speed of light would require infinite energy, which is why no massive object can ever do so. From a physical perspective, this limit emerges from the structure of relativistic equations, particularly from the way mass and energy are related. From a computational perspective, the limit might emerge from the simulation's resource constraints. As an object moves faster, more computation is required to track its trajectory, to update its position, to handle the relativistic effects on its time and length. The simulation simply cannot allocate enough resources to handle objects moving at or beyond the speed of light, and so it imposes a hard limit that prevents any such situation from arising. This interpretation has implications for how we think about the structure of the universe. If the speed of light is a feature of the underlying simulation rather than a property of physical reality, then we should expect to find other signs of the simulation's resource constraints. We should expect to see the universe imposing limits whenever resource-intensive situations would otherwise arise. And in fact, we do see this in several different ways. One example is the behavior of black holes. When matter is compressed into a sufficiently small region, gravity becomes so strong that not even light can escape. The boundary of this region, the event horizon, marks a kind of computational firewall. Information that crosses the event horizon cannot affect anything outside it. Whatever is happening inside a black hole is, from the perspective of the rest of the universe, irrelevant and uncomputable. This is precisely the kind of optimization that a simulation might use to manage extreme situations. Rather than tracking the detailed evolution of matter under conditions of infinite density, the simulation hides the interior behind an event horizon and computes only the external properties of the black hole, its mass, its charge, and its angular momentum. Stephen Hawking and others have shown that black holes can be fully described by these three external parameters, a result known as the no-hair theorem. From a computational perspective, this is exactly what we would expect if the simulation were saving resources by suppressing the internal complexity of black holes. Another example is the cosmic horizon. The observable universe has a finite size, not because the universe itself is necessarily finite, but because light from beyond a certain distance has not had time to reach us since the beginning of the universe. Beyond this horizon, there may be regions of space that are forever inaccessible, not just to our instruments, but to any influence whatsoever. From a physical perspective, the cosmic horizon is a consequence of the finite age of the universe combined with the finite speed of light. From a computational perspective, the cosmic horizon is a kind of natural boundary on the simulation. The simulation does not need to compute the detailed behavior of regions that cannot affect us, and so it might not. Whether or not regions beyond the cosmic horizon are real in the same sense as the regions we can observe is a question that current science cannot answer. But the existence of such horizons fits naturally with the picture of a universe that allocates computational resources only to regions that matter. The speed of light, then, may be more than just a maximum velocity. It may be a window into the architecture of reality itself. The universe operates with a fundamental clock speed, propagating influences at a fixed rate per unit of time. It enforces resource limits that prevent infinite computational requirements from arising. It establishes horizons that bound the regions of space that need to be tracked in detail. All of these features are exactly what we would expect from a sophisticated simulation running on finite hardware. Whether the universe actually is such a simulation, or whether these features have other explanations rooted in the deeper laws of physics, remains an open question. But the picture that emerges is one of a universe whose architecture closely resembles that of a computational system, with all the constraints, optimizations, and trade-offs that such a system would entail. Yet this evidence raises new scientific questions. If the universe operates within constraints suggestive of a finite computational substrate, what else might we expect to find? What other features should reveal themselves to careful examination? The investigation continues, and the next layer involves something even more remarkable. The fact that the universe, at its most fundamental level, appears to be made not of substance but of mathematics. And mathematics, more than anything else, is the language of computation. There is a peculiar fact about the universe that has troubled thoughtful observers for centuries. The same abstract mathematics that humans developed to count sheep, divide land, and predict the seasons turns out, upon careful examination, to describe the deepest workings of physical reality with a precision that borders on the supernatural. Equations that were derived purely from logical principles, with no reference to any physical phenomenon, turn out to predict the behavior of subatomic particles, the structure of galaxies, and the propagation of light to accuracies that exceed the limits of our most sensitive instruments. This is not how one would expect a physical universe to behave. It is, however, exactly how one would expect a computed universe to behave. The physicist Eugene Wigner, in a now famous essay published in 1960, called this phenomenon the unreasonable effectiveness of mathematics in the natural sciences. Wigner pointed out that mathematics is, on the face of it, a purely abstract human activity. Mathematicians prove theorems by manipulating symbols according to rules of logic. They are not, when doing this work, paying attention to the physical world. They are exploring the consequences of definitions and axioms. Yet again and again throughout history, the abstract structures discovered by mathematicians have turned out to describe physical reality with extraordinary precision. The conic sections, studied by ancient Greek mathematicians as a purely geometric exercise, turned out to describe the orbits of planets. The non-Euclidean geometries developed in the 19th century as logical curiosities turned out to describe the structure of space-time in general relativity. The complex numbers invented to solve algebraic equations that had no real solutions turned out to be essential to the formulation of quantum mechanics. This pattern is not occasional, it is pervasive. In nearly every branch of fundamental physics, the mathematics that turned out to be needed was developed years, decades, or centuries before its physical application was understood. Group theory, developed in the 19th century to study the symmetries of algebraic equations, became central to particle physics in the 20th century. Tensor calculus, developed by mathematicians in the late 19th century, became the language of general relativity. The mathematical theory of fiber bundles, developed in the mid-20th century as an abstract topological structure, became essential to gauge theory, the framework that describes all of the fundamental forces except gravity. Time and again, mathematicians stumble across structures that have no obvious connection to physical reality, only to discover later that those structures are exactly what physics requires. If the universe were a purely physical system with no underlying connection to mathematical abstraction, this pattern would be inexplicable. There is no obvious reason why physical reality should be describable by elegant mathematical equations at all. We could imagine a universe that was simply too complex for any mathematical description, a universe whose behavior could only be observed and recorded, but never compressed into formulas. We could imagine a universe whose laws required impossibly cumbersome equations with thousands of terms and exceptions, defying any attempt at simplification. Instead, we find a universe whose deepest laws can be written on a single sheet of paper, and whose constants and parameters are surprisingly few. The fundamental equations of physics taken together are remarkable for their brevity. The equations of general relativity, the equations of the standard model of particle physics, the equations of quantum mechanics, all fit comfortably on a single chalkboard. They describe phenomena ranging from the behavior of individual electrons to the evolution of the entire observable universe. This compactness is one of the most surprising features of physical law. It is not a feature we have any independent reason to expect, and it is one of the strongest pieces of indirect evidence for the simulation hypothesis. A computed universe would have to be governed by a finite set of rules expressed in some form of code. Those rules would, by necessity, be compact because longer rules would require more storage and more processing power. The most efficient simulation would be one whose underlying laws could be expressed in the smallest possible number of mathematical statements. And this is exactly what we observe. The universe behaves as if it is being computed by a program that has been carefully optimized for compactness. The mathematical universe hypothesis, proposed by the cosmologist Max Tegmark, takes this observation to its logical extreme. Tegmark argues that the unreasonable effectiveness of mathematics is unreasonable only if we assume that the universe is fundamentally physical and only secondarily mathematical. If we reverse the assumption, if we suppose that the universe is fundamentally mathematical and only appears to be physical, then the effectiveness of mathematics becomes entirely reasonable. The universe is mathematics. Physical reality is just what mathematical structures look like from the inside. There is nothing else to the universe beyond the mathematics that describes it. This view is radical, and it is not universally accepted, but it has the virtue of explaining a fact that other views struggle to explain. If the universe is mathematics, then mathematics describes the universe perfectly, because there's nothing more to describe. There is no underlying physical substance separate from the equations. The equations are the universe. From the perspective of the simulation hypothesis, this view is closely related to the idea that the universe is a computation. A computation, after all, is just the systematic application of mathematical rules to a set of data. If the universe is a computation, then it is also, in a meaningful sense, a mathematical structure. The two views differ in their details, but they agree on the central point. Reality, at its deepest level, is informational rather than material. This shift in perspective is reflected in the evolution of physics itself. Throughout the 20th century, physicists have moved increasingly toward viewing information as the fundamental substance of the universe. The concept of entropy, originally developed in the 19th century to describe the behavior of heat, was reformulated by Claude Shannon in the mid-20th century as a measure of information. The two formulations turned out to be mathematically identical, suggesting that thermodynamics and information theory are describing the same underlying reality. The black hole entropy formula, derived by Stephen Hawking and Jacob Bekenstein, expresses the information content of a black hole in terms of its surface area. The holographic principle, which we will examine in greater detail later, suggests that all the information in any region of space can be encoded on the boundary of that region, treating space itself as a kind of data structure. The physicist John Wheeler captured this trend with a memorable phrase. He proposed that the universe is built not from matter, not from energy, not from any kind of substance, but from information. He summarized this view with the phrase "it from bit," suggesting that every physical entity, derives its existence from the answers to yes or no questions, that is, from bits of information. On this view, the universe is fundamentally a vast collection of bits, organized according to mathematical rules, evolving over time according to the operations of those rules. Matter and energy are not the basic constituents of reality. They are emergent properties of the underlying informational structure. If this view is correct, then the distinction between physical reality and a simulated reality becomes considerably less clear. A simulation is, by definition, a mathematical structure being computed. If the universe is also fundamentally a mathematical structure being computed, then the universe is, in some sense, already a simulation, regardless of whether it is being run by an external civilization. The question is not whether the universe is a simulation. The question is what kind of simulation it is, and whether the substrate on which it runs is physical, mathematical, or something else entirely. This perspective has practical consequences for science. If the universe is fundamentally mathematical, then the project of physics is the project of discovering the mathematical structure that describes reality. The physical phenomena we observe are not the ultimate object of study. They are clues that point toward the underlying equations. Once those equations are fully understood, physics will have completed its task, and there will be nothing left to discover beyond the consequences of the equations themselves. This view is sometimes called the theory of everything, the idea that there exists a single mathematical framework that, in principle, accounts for all physical phenomena. The search for such a theory has been a central goal of theoretical physics for over a century, and although it has not yet succeeded, the assumption that it is possible is itself a vote of confidence in the mathematical nature of reality. There is, however, an interesting twist to this story. The mathematician Kurt Gödel proved in the 1930s that any sufficiently powerful mathematical system contains true statements that cannot be proven within the system itself. This result, known as Gödel's incompleteness theorem, has profound implications for any project that attempts to capture all of reality in a single mathematical framework. If the universe is fundamentally mathematical, and if Gödel's theorem applies to whatever mathematical structure underlies it, then there are truths about the universe that cannot, in principle, be derived from any finite set of rules. This places a kind of fundamental limit on what we can know about reality, even if we have access to the complete set of underlying equations. For the simulation hypothesis, this raises an interesting possibility. If the universe is being computed by an external system, then the rules governing that computation may be subject to the same kinds of limitations that apply to any formal mathematical system. There may be aspects of the simulation that even its programmers cannot fully predict, properties that emerge from the computation itself rather than from the rules that initiated it. The universe might contain genuine novelty, genuine surprise, even from the perspective of whatever system is running it. This is a strange thought, but it is consistent with the mathematical structure of the situation, and it suggests that the question of whether we live in a simulation may be less important than the question of what kind of simulation is even possible to run. If the universe is a computation, then like every computation ever performed, it should occasionally produce errors. Software, no matter how sophisticated, contains bugs. Hardware, no matter how reliable, suffers from imperfections. Even the most carefully engineered systems, running on the most advanced equipment, eventually encounter conditions their designers did not anticipate. The history of computing is, in many ways, the history of debugging. From the earliest mainframes to the latest supercomputers, every machine ever built has produced unexpected behavior, and every program ever written has revealed some flaw upon sufficient testing. There is no reason to believe that a simulation of an entire universe would be exempt from this universal pattern. If anything, the unimaginable complexity of such a simulation would make errors more likely, not less. What would such errors look like viewed from inside the simulation? This is one of the most intriguing questions raised by the simulation hypothesis, and it has prompted a small but serious community of researchers to examine reality for signs of computational imperfection. The challenge, of course, is that any error in a simulation would, by definition, be inconsistent with the normal rules of physics. From the inside, a glitch would appear as a violation of natural law, a moment when something happened that should not have been possible. Such moments are exactly what science traditionally investigates in the form of unexplained phenomena, statistical anomalies, and observations that resist conventional explanation. Most of these turn out to have ordinary causes, eventually revealed by further investigation. But some have remained unexplained for decades, and a few have features that, viewed through the lens of the simulation hypothesis, look uncomfortably like rendering errors. Consider the curious case of certain quantum measurement results. The mathematics of quantum mechanics predicts the probabilities of various outcomes, but the specific outcome of any individual measurement is fundamentally random. There is no hidden variable, no underlying mechanism that determines which outcome will actually occur. Or so the standard interpretation tells us. Several physicists, including the late John Bell, have established mathematical theorems that constrain what kinds of hidden mechanisms could be operating, and the experimental evidence rules out most classical possibilities. But these constraints leave open the possibility that the apparent randomness of quantum measurements arises from a process more complex than pure chance. If the universe is being computed, then quantum randomness might be the output of a pseudo-random number generator, an algorithm that produces numbers that appear random but are actually determined by some underlying state. Such algorithms are used in every digital simulation because true randomness is computationally expensive, while pseudo-randomness can be generated efficiently. If quantum randomness is actually pseudo-randomness, then it should, in principle, exhibit certain statistical signatures that distinguish it from true randomness. Various researchers have examined large datasets of quantum measurement outcomes, looking for patterns that might reveal the underlying algorithm. So far, no clear patterns have emerged. The quantum world appears to be statistically indistinguishable from genuine randomness, at least at the level of detail we have been able to examine. But the search continues, and some researchers have suggested that with sufficiently large datasets and sufficiently powerful analysis techniques, hidden patterns might eventually be revealed. The discovery of such a pattern would be one of the most significant scientific findings in history, suggesting that the apparent unpredictability of the quantum world is actually the output of a deterministic computation. Beyond the realm of quantum measurement, there are other phenomena that some researchers have interpreted as possible computational artifacts. The cosmic microwave background, the faint radiation left over from the early universe, has been mapped with extraordinary precision over the past several decades. Some statistical analyses of this radiation have revealed peculiar patterns, including alignments and asymmetries that should not exist if the universe is truly homogeneous on large scales. These features, sometimes called the axis of evil, due to their suggestive but ill-understood directional alignment, have resisted conventional explanation for years. Various theories have been proposed, ranging from systematic errors in the measurements to exotic physical processes in the early universe. None has gained widespread acceptance. From the perspective of the simulation hypothesis, these patterns might represent imprints of the computational structure itself, evidence that the universe is being rendered on some kind of grid or lattice that does not perfectly preserve the symmetry it is intended to simulate. Another category of potential anomalies involves the fine details of physical constants. The fundamental constants of nature, things like the strength of gravity, the charge of the electron, and the speed of light, are measured to extraordinary precision. They appear to be exactly the same throughout the observable universe and to have been the same throughout cosmic history. Or do they? Some careful measurements, particularly involving the fine structure constant, which governs the strength of electromagnetic interactions, have suggested that this constant might vary by tiny amounts across different regions of space or different epochs of time. The evidence is contested, and the variations, if they exist, are extremely small. But they are precisely the kind of subtle inconsistency that one might expect from a simulation that is rendering the universe with finite precision, where small numerical errors accumulate over time or across distance. There are also more mundane categories of unexplained phenomena that have caught the attention of researchers interested in the simulation hypothesis. Reports of unusual physical events, things like ball lightning, unexplained luminous phenomena, and certain kinds of localized gravitational anomalies have been documented for centuries. Most of these reports turn out to have ordinary explanations, things like atmospheric phenomena, optical illusions, or simple measurement errors. But a few resist explanation, and some have features that strain the boundaries of known physics. The temptation to interpret these as glitches in a simulation is strong, but it is a temptation that careful researchers resist. The history of science is full of phenomena that were initially considered inexplicable and were later found to have ordinary causes. The lesson is that one should not invoke extraordinary explanations until ordinary ones have been thoroughly ruled out. Still, even with this skeptical caveat, there is a serious methodological question raised by the simulation hypothesis. How would we know if we encountered a genuine glitch as opposed to an unusual but ultimately explicable physical phenomenon? The answer is not obvious. A glitch in a simulation would, by definition, be a deviation from the normal rules of the simulation. From inside, this would appear as a deviation from the laws of physics. But not every apparent deviation from physical law is a glitch. Some are signs that our understanding of physical law is incomplete. The discovery of new phenomena, things like radioactivity, dark matter, or gravitational waves, often initially appears as a violation of established theory, only to later be incorporated into a deeper theoretical framework. To distinguish a genuine glitch from a new physical phenomenon would require establishing that the deviation in question cannot be explained by any consistent extension of physical law. This is, in practice, an extremely difficult standard to meet. Almost any unexplained phenomenon could, in principle, be the result of physics we do not yet understand. To classify something as a glitch, we would need to show not just that current physics cannot explain it, but that no possible extension of physics could explain it. This requires a kind of negative proof that is notoriously difficult to establish. As a result, even the most suggestive anomalies remain ambiguous, capable of being interpreted as either signs of deeper physics or as signs of computational error, depending on one's prior assumptions. Still, the search for glitches has produced some interesting candidate phenomena, even if none has been conclusively identified as such. One category that has attracted particular attention involves the behavior of high-energy cosmic rays. These are particles, mostly protons, that arrive at Earth from deep space with energies far greater than anything we can produce in laboratories. The highest energy cosmic rays carry energies many orders of magnitude greater than the highest energy particles produced in our most powerful accelerators. When such a particle interacts with the atmosphere, it produces a cascade of secondary particles that can be detected by ground-based observatories. The statistical distribution of cosmic ray energies has been carefully mapped, and it shows a sharp cutoff at extremely high energies, called the GZK cutoff, that is consistent with theoretical predictions. But there have been a small number of events that appear to exceed this cutoff, particles arriving with energies that should not be possible according to current physics. These events are rare, and they may represent measurement errors, but they have prompted serious theoretical investigation, with some researchers suggesting that they might require modifications to the laws of physics at extreme energy scales. From the perspective of the simulation hypothesis, they might represent moments where the simulation has miscalculated, allowing particles to acquire energies that violate the normal rules. Another category of suggestive phenomena involves the behavior of certain quantum systems at large scales. The boundary between the quantum world, where superposition and entanglement are routine, and the classical world, where objects have definite properties, is poorly understood. Most physicists assume that quantum behavior should extend to all scales, with classical behavior emerging from the statistical averaging of many quantum interactions. But there have been experiments that show quantum behavior in systems much larger than the typical microscopic scale, including certain biological molecules and small mechanical oscillators. Whether these experiments push us toward understanding the quantum classical boundary or whether they reveal something stranger about the universe's computational structure remains an open question. What is clear is that the universe behaves, in many respects, as if it is making decisions about when to render quantum effects and when to allow classical behavior to dominate. Such decisions, in a simulation, would be implemented through algorithms that determine the level of detail at which different parts of the simulation are computed. The transition from quantum to classical behavior might be precisely such an algorithm, operating at scales we have only begun to investigate. Beyond the realm of physics, there is another category of potential evidence for simulation imperfection that has emerged not from laboratories, but from the collective experiences of ordinary people. It is a phenomenon that has been studied seriously by psychologists, dismissed by skeptics, and embraced enthusiastically by proponents of the simulation hypothesis. It is known as the Mandela effect, and it refers to the curious tendency of large numbers of people to share identical false memories about specific cultural facts. The phenomenon is named after Nelson Mandela, the South African leader who, despite being released from prison in 1990 and serving as president of South Africa from 1994 to 1999 before dying in 2013, is remembered by many people as having died in prison during the 1980s. The number of people who share this specific false memory in identical detail has been the subject of considerable curiosity. The standard explanation for the Mandela effect, accepted by most psychologists, is that it represents a particularly vivid example of how human memory works. Memory is not, as we tend to imagine, a recording device that faithfully preserves the past. It is a reconstructive process in which the brain assembles a coherent narrative from fragmentary impressions, contextual cues, and prior expectations. This reconstruction is subject to systematic biases. We remember things that fit our expectations more easily than things that contradict them. We confuse details from different sources, attributing characteristics from one context to another. We are influenced by social cues, adopting the memories of others in place of our own. Given these well-documented features of human cognition, it is not surprising that large numbers of people would converge on identical false memories about cultural facts. The convergence reflects shared expectations and shared confusions, not any deeper truth about the structure of reality. This explanation is reasonable, and it accounts for most cases of the Mandela effect, but there are aspects of the phenomenon that are not fully explained by ordinary cognitive science. The specificity of the false memories, the consistency of details across millions of independent observers, and the persistence of the memories, even when contradicted by clear evidence, all suggest that something more than ordinary memory error may be at play. The most famous example, beyond Mandela himself, is the spelling of a popular series of children's books. Millions of people remember these books being titled with one spelling, while the actual title uses a slightly different spelling. The discrepancy is small, but it is consistent across an enormous number of people, many of whom have specific memories of seeing the title in print. Other examples include details of corporate logos, memorable lines from films, the appearance of certain landmarks, and historical events of various kinds. In each case, large numbers of people share specific false memories, and the false memories tend to be more vivid and more consistent than ordinary cognitive errors would predict. The pattern has prompted some researchers, particularly those interested in the simulation hypothesis, to propose an alternative explanation. What if the false memories are not actually false? What if they accurately reflect a previous state of the simulation, a state that was changed at some point by an update or an edit, leaving residual memories in observers who experienced the previous state? This interpretation requires a particular view of how a simulation might work. It supposes that the simulation is updated periodically, with new versions overwriting old ones, and that the memories of observers within the simulation might be partially preserved across updates. If most details are correctly synchronized between the new and old versions, but some small details are missed, then observers would experience the world as having always been in its current state, while retaining ghost memories of the previous state. The Mandela effect on this interpretation is not a cognitive error. It is a kind of bleed-through, evidence that the universe has been edited and that the editing has not been perfectly clean. This is a fascinating idea, and it has captured the imagination of many people interested in the simulation hypothesis. But it is important to be careful about how seriously to take it. The hypothesis is, almost by definition, unfalsifiable. Any apparent inconsistency between memory and reality can be interpreted either as a cognitive error or as a simulation update, with no clear way to distinguish between the two. Without some independent method of testing the hypothesis, it remains in the realm of speculation. And the cognitive science explanation, while perhaps less exciting, has the advantage of being grounded in well-established research about how human memory actually works. There are, however, certain features of the Mandela effect that the cognitive science explanation does not fully capture. One is the specificity of the memories. People do not generally have vague impressions of the false versions. They have detailed recollections, sometimes including specific contexts in which they encountered the false information. They remember reading the misspelled title on a particular book in their childhood home. They remember seeing the inaccurate logo on a specific product at a specific store. These are not the kinds of memories that ordinary cognitive errors typically produce. Ordinary memory errors tend to be vague, uncertain, and easily corrected when confronted with evidence. Mandela effect memories tend to be vivid, specific, and resistant to correction even when the evidence is clear. Another feature that the standard explanation does not fully capture is the social dimension of the phenomenon. Mandela effects tend to cluster around specific cultural items, with large numbers of people independently arriving at the same false memory. The cognitive science explanation accounts for this in terms of shared expectations and cultural cues, but the cluster effects can be remarkably tight. Specific false memories appear at specific frequencies in the population, with statistical regularities that some researchers find surprising. Whether these regularities reflect underlying patterns in human cognition or something stranger is not entirely clear. A third feature is the relationship between Mandela effects and other anomalous experiences. People who report Mandela effect memories often also report other unusual experiences, including déjà vu, premonitions, and a general sense that reality is somehow not quite what it seems. Whether these correlations reflect a common psychological tendency to perceive anomalies, or whether they reveal something genuine about a class of observers who are particularly sensitive to inconsistencies in reality, is a question that current research has not definitively answered. The hypothesis that some people are more attuned to simulation glitches than others is, of course, a speculative one. but it is consistent with the observation that anomalous experiences tend to cluster in specific individuals. To approach the Mandela effect with appropriate scientific rigor, one must consider both the conventional explanation and the simulation interpretation as hypotheses to be tested. The conventional explanation is well supported by cognitive science research and accounts for most cases. The simulation interpretation is intriguing but lacks direct empirical support. Neither hypothesis on its own provides a complete account of the phenomenon. The most reasonable position is to acknowledge that human memory is fallible and frequently produces collective errors, while remaining open to the possibility that some specific cases might require explanations beyond ordinary cognitive science. What makes the Mandela effect particularly interesting from the perspective of the simulation hypothesis is that it points to a class of potential evidence that does not depend on physical measurements. If the universe is a simulation, then the simulation must in some way track and update the memories of conscious observers within it. Any inconsistency in this tracking would manifest as inconsistencies in subjective experience, including memory. The search for evidence of a simulation, on this view, is not just a matter of looking for anomalies in physics. It is also a matter of examining the structure of consciousness itself, looking for signs that subjective experience is not fully consistent with the supposed objective reality. This is, of course, a difficult and treacherous area of inquiry. Subjective experience is notoriously hard to study scientifically, and any claims about inconsistencies in memory or perception must be approached with extreme caution. The history of paranormal research is full of cases in which apparent anomalies turned out to be the result of cognitive biases, methodological errors, or outright fraud. The lesson is that extraordinary claims require extraordinary evidence, and that the burden of proof is on those who would assert that ordinary cognitive errors are actually evidence of simulation glitches. Still, the question of whether collective memory errors might sometimes reflect something stranger than ordinary cognition is one that deserves at least a measured and careful examination, even if the conclusion is ultimately that they do not. Closely related to the Mandela effect and often discussed in the same contexts is another phenomenon that has long puzzled both scientists and ordinary people. It is the experience of déjà vu, the sudden and powerful feeling that the present moment has happened before. The experience is brief, usually lasting only a few seconds, but during that time it can be remarkably vivid. People report a strong sense of recognition, a feeling that they know exactly what is about to happen, that they have lived this exact moment before in every detail. The feeling is often accompanied by a sense of strangeness, a recognition that the experience is somehow not quite right, even as it unfolds. Most people have experienced déjà vu at some point in their lives, and surveys suggest that the phenomenon occurs more frequently in younger people, decreasing in frequency with age. The conventional scientific explanation for déjà vu, accepted by most neuroscientists, is that it represents a brief malfunction in the brain's memory system. The brain processes incoming sensory information through multiple parallel channels, with different regions handling different aspects of the experience. Normally, these channels are synchronized, producing a unified perception of the present moment. Occasionally, the synchronization breaks down briefly, with one channel processing the information slightly faster than the others. The result is that part of the brain perceives the experience as a memory before the rest of the brain perceives it as a present event, creating the sensation of having experienced the moment before. This explanation is supported by neuroimaging studies and by the observation that déjà vu is more common in people with certain types of brain disorders, particularly forms of epilepsy that affect the temporal lobes, which are involved in memory processing. This explanation, like the cognitive science account of the Mandela effect, is reasonable and well supported by evidence. But also, like the Mandela effect, it does not account for every aspect of the phenomenon. Some experiences of déjà vu are accompanied by accurate predictions about what is about to happen, predictions that can be verified after the fact. Some involve specific details that the experiencer claims could not have been known in advance. Most of these claims, on careful examination, turn out to be the result of memory bias, with people reconstructing their déjà vu experiences after the fact to align with what actually occurred. But not all such claims can be dismissed in this way, and the phenomenon retains an element of mystery that the standard explanation does not fully resolve. From the perspective of the simulation hypothesis, déjà vu might represent something more than a neural glitch. It might be a brief moment of desynchronization between the simulation and the observer, a flicker of recognition that occurs when the simulation briefly repeats or revisits a previously computed state. To take seriously the possibility that we live in a simulation, one must eventually confront a practical question. Could such a thing actually be done? The simulation hypothesis is not just a philosophical exercise. It makes a specific claim about the kind of computational resources required to produce a convincing universe, and that claim can be examined quantitatively. If the resources required are impossibly large, then the hypothesis becomes correspondingly less plausible. If the resources required are large but not impossibly so, then the hypothesis must be taken seriously as a real possibility. Several researchers have undertaken this kind of analysis, and their conclusions are revealing. The first thing to understand is what would actually need to be simulated. A common misconception is that simulating the universe would require tracking every particle in every region of space at every moment in time. This is not necessarily the case, and indeed it would be enormously wasteful to do so. A well-designed simulation would track only what is necessary for the experiences of conscious observers. Regions of space that are not being observed would not need to be computed in detail. Times and places that are not affecting the observed universe could be left in a simplified state or not computed at all. The level of detail at which any given region is rendered would depend on the proximity and attention of conscious observers within the simulation. This kind of selective rendering is exactly how modern video games operate, and there's no reason to assume that a simulated universe would not employ similar optimizations. Even with such optimizations, however, the computational requirements would be vast. Conservative estimates suggest that simulating the brain of a single human being at sufficient resolution to reproduce all of its conscious experiences would require something on the order of 10 to the 18 operations per second. Simulating the entire population of Earth at this level of detail would require something on the order of 10 to the 27 operations per second. Simulating the immediate physical environment that each of these brains interacts with at the level of detail required to produce convincing sensory experiences would add another factor of perhaps 10 to the 10 to 10 to the 20 operations per second, depending on the level of detail at which the environment is rendered. Adding in the cosmic environment, the distant stars and galaxies that are visible to telescopes would add additional but smaller computational costs, since the level of detail required for distant objects is much lower than for nearby objects. The total computational requirements, then, are somewhere in the range of 10 to the 28 to 10 to the 30 operations per second, depending on the assumptions one makes about the level of detail required and the efficiency of the simulation. This is, by any conventional standard, an enormous number. It is many orders of magnitude beyond the capabilities of any computer that currently exists, or that humanity is likely to build in the foreseeable future. The most powerful supercomputers in the world today operate at speeds of around 10 to the 18 operations per second, and they require buildings full of equipment and significant amounts of power to do so. To run a simulation of the kind described above would require a computer many orders of magnitude more powerful than anything currently available. But the question is not whether humanity could build such a computer. The question is whether any civilization anywhere in the universe could build such a computer. And here the analysis becomes more interesting. The fundamental physical limits on computation are remarkably permissive. The physicist Seth Lloyd, in a 2000 paper, calculated the maximum computational capacity of a 1 kilogram, 1 liter computer, given only the constraints of fundamental physics. His result was that such a computer could, in principle, perform around 10 to the 51 operations per second while storing around 10 to the 31 bits of information. This is 22 orders of magnitude beyond what we would need to simulate human civilization, and it could be done with a single small device, not a galaxy-spanning megastructure. Of course, no one currently knows how to build a computer that approaches these fundamental limits. Our current technology is many orders of magnitude less efficient than the theoretical maximum. But the point is that the limits are not set by what we currently know how to do. They are set by the underlying physics of computation, and those limits are extraordinarily generous. A civilization that has mastered the physics of computation, even to a small fraction of its theoretical potential, would have access to computational resources that vastly exceed what would be required to simulate any number of universes containing any number of conscious observers. If we imagine a civilization that has access not just to a single optimized computer, but to the resources of an entire star system, the available computational power becomes truly staggering. Such a civilization, sometimes called a Kardashev Type 2 civilization, would have access to all the energy produced by its star, which for a sun like our own is around 10 to the 26 watts. Converting this energy into computation at theoretical efficiency would yield around 10 to the 56 operations per second, sufficient to simulate the entire history of human civilization in full detail in a fraction of a second. A civilization with access to the resources of an entire galaxy, a Kardashev Type 3 civilization, would have access to computational resources greater than this by another 10 orders of magnitude. The numbers quickly become so large that the question of whether a particular simulation is feasible becomes essentially trivial. For any sufficiently advanced civilization, simulating universes is not a major undertaking. It is a matter of routine. This analysis has important implications for the simulation hypothesis. It suggests that if any sufficiently advanced civilization exists anywhere in the universe, then simulations of universes like our own are not just possible but inevitable. The resources required are minimal compared to the resources available. The motivations for running such simulations, including scientific research, education, entertainment, and historical reconstruction, are likely to be present in any civilization that values knowledge or experience. The combination of feasibility and motivation makes it highly probable that if advanced civilizations exist, they would run simulations. And if they would run simulations, then the number of simulated universes would vastly exceed the number of natural universes, returning us to the statistical argument that Bostrom made in his original paper. There are objections to this line of reasoning, and they are worth considering carefully. One objection is that consciousness may not be substrate independent, that subjective experience may require a specific physical substrate that cannot be replicated in computation. If this is true, then no matter how powerful a computer is, it cannot generate genuine consciousness, and the question of how many simulated minds exist becomes irrelevant. This is essentially the position taken by philosophers like John Searle, and it has been defended at length. The opposing view, called computational functionalism, holds that consciousness is whatever process performs certain functional roles, and that any substrate that performs those roles will generate consciousness regardless of its physical nature. The debate between these two positions has not been resolved, and it may not be resolvable through philosophical argument alone. What can be said is that the question is open, and that the simulation hypothesis depends on the computational functionalist view being correct, at least in some form. Another objection involves the nested simulation problem. If advanced civilizations can run simulations, then those simulations themselves might contain advanced civilizations capable of running their own simulations, and so on indefinitely. The result would be an infinite hierarchy of nested simulations, each one consuming the resources of the level above it. This nesting would seem to require infinite computational resources at the top of the hierarchy, which is impossible. The objection has some force, but it can be addressed by noting that simulations need not be exact replicas of their host environments. A simulation might be run at lower resolution than its host, with fewer conscious observers and less detailed physics. Each level of nesting would consume only a small fraction of the resources of the level above it, allowing for a finite but potentially very deep hierarchy. The total computational requirements would be finite, even if the number of nesting levels is large. A third objection involves the question of what kind of computer would be doing the simulating. We naturally tend to imagine computers like our own, made of silicon chips and electronic circuits. But the actual substrate of a hypothetical simulator might be quite different. It might be based on quantum mechanics, using superposition and entanglement to perform computations that classical computers cannot. It might be based on more exotic physics, using phenomena that we have not yet discovered. It might be based on physical processes that we do not currently classify as computation at all. The point is that when we estimate the computational requirements of simulating a universe, we are making assumptions about the kind of computation involved. Different assumptions might lead to radically different estimates. The deeper question is not how much computation is required, but what counts as computation in the first place. These complications notwithstanding, the basic conclusion of the resource analysis is clear. Simulating a universe is not, in principle, beyond the reach of an advanced civilization. The computational requirements are large, but they are finite, and they are well within the limits set by fundamental physics. Whether any civilization actually has the resources, the technology, and the motivation to perform such simulations is unknown. But the possibility cannot be ruled out on practical grounds, and the implications, if it is even occasionally done, are profound. We may not be in a simulation, but the universe is the kind of thing that could be simulated, and we have no reliable way to determine from the inside whether or not it actually is. If we live in a simulation, then there is one element of our experience that presents a particularly difficult challenge to explain. That element is consciousness itself, the inner subjective awareness that each of us possesses, the sense of being someone who experiences the world rather than merely processing information about it. Consciousness has long been considered one of the deepest unsolved problems in philosophy and science, and the simulation hypothesis adds a new layer to that problem. If the universe is a computation, then consciousness must somehow arise from that computation. But how exactly does subjective experience emerge from the manipulation of bits? This question, sometimes called the hard problem of consciousness, has resisted satisfying answers for as long as it has been asked. The conventional scientific approach to consciousness treats it as an emergent property of certain kinds of physical systems, particularly biological brains. The brain is, on this view, a kind of biological computer, processing information from the senses, generating responses to that information, and producing the various phenomena we associate with mental life. Consciousness arises somehow from the activity of the brain, though the precise mechanism by which this happens is not yet understood. The hard problem of consciousness, as articulated by the philosopher David Chalmers, is the problem of explaining why this emergence should occur at all. Why should any physical process give rise to subjective experience? Why is there something it is like to be a conscious being rather than nothing? These questions cannot be answered by simply describing the physical processes involved. The physical description, no matter how complete, seems to leave out something essential about the experience itself. This problem becomes particularly acute in the context of the simulation hypothesis. If we accept that the universe is a computation, then we must accept that consciousness arises somewhere within the computation. But where exactly does it arise? Does every computational process generate consciousness, or only certain kinds? If only certain kinds, what distinguishes those that do from those that do not? These questions have practical consequences because they bear on whether the conscious beings within a simulation are equivalent to the conscious beings outside it. If consciousness can arise in any sufficiently sophisticated computation, then a simulation can contain genuine subjects of experience, beings whose inner lives are real and whose suffering or joy matters morally. If consciousness requires a specific substrate, then simulated beings might be philosophical zombies, behaving as if they were conscious without actually having any inner experience. The view that consciousness can arise in any sufficiently complex information processing system is called computational functionalism, and it is the working assumption of much of contemporary philosophy of mind. On this view, consciousness is not tied to any particular physical substrate. It is a functional property defined by the kinds of operations a system performs rather than by what the system is made of. A brain made of biological neurons can be conscious. A brain simulated on a digital computer with the same functional organization would also be conscious. A brain implemented on some entirely different substrate, perhaps using quantum effects or some exotic physics we have not yet discovered, would also be conscious, provided it performed the same functional operations. The substrate is irrelevant. What matters is the pattern. This view has many proponents, but it also has serious critics. The most famous critique is the Chinese room argument, proposed by the philosopher John Searle in 1980. Searle invites us to imagine a room in which a person who does not understand Chinese is given a set of rules for manipulating Chinese characters. The rules are sufficiently sophisticated that, when given any string of Chinese characters as input, the person can produce a string of Chinese characters as output that would be a sensible response in Chinese. From outside the room, it would appear that the room understands Chinese, but the person inside the room, Searle argues, does not understand Chinese at all. They are merely manipulating symbols according to rules. The symbol manipulation, no matter how sophisticated, does not produce understanding. Therefore, the Chinese room argument concludes, computational processes cannot produce genuine understanding, and presumably cannot produce genuine consciousness either. There is something missing from any purely computational account of mind, something that biological brains have and computers, no matter how sophisticated, do not. The Chinese room argument has generated decades of debate with responses on both sides. Computational functionalists have argued that while the person inside the room does not understand Chinese, the room as a whole, including the person and the rules, does understand Chinese, and that this understanding is what corresponds to consciousness. Critics have argued that this response merely shifts the problem without solving it, that it is unclear how a system as a whole can possess properties that none of its parts possess. The debate has not been resolved, and it may not be resolvable through philosophical argument alone. For the simulation hypothesis, the implications are significant. If computational functionalism is correct, then simulations can contain genuine conscious beings, and the hypothesis that we are inside such a simulation becomes a serious possibility. If computational functionalism is incorrect, then simulations cannot contain genuine consciousness, and the question of whether we are inside one becomes moot. We are conscious, after all, and if our consciousness cannot be reproduced in a simulation, then we cannot be inside one. But the situation is not quite this simple. Even if consciousness requires a specific physical substrate, that substrate might be something that exists in both our world and the world of any potential simulators. If consciousness arises from quantum effects, for example, then any sufficiently advanced computer that can manipulate quantum states might be able to produce consciousness, regardless of whether it is digital or biological. The question of whether a simulation can contain consciousness depends on the details of how consciousness actually works, which we do not yet understand. What can be said with some confidence is that consciousness is, in some sense, the central mystery of the simulation hypothesis. If we accept the hypothesis, we must accept that consciousness can arise in computational systems. If we reject the hypothesis on the grounds that consciousness cannot arise in computational systems, we must explain what makes biological consciousness different from any possible computational equivalent. Either way, consciousness is the pivot on which the entire question turns. There's another aspect of consciousness that bears on the simulation hypothesis, and it concerns the structure of subjective experience itself. When we examine our own minds carefully, we find that subjective experience has a curious quality. It is not a faithful representation of the physical world. It is a constructed model assembled by the brain from sensory inputs, expectations, and memories. The colors we see are not properties of the physical world. They are interpretations our brains construct from electromagnetic radiation in certain wavelengths. The sounds we hear are not properties of the physical world. They are interpretations our brains construct from pressure waves in the air. Our entire experience of the world is, in a real sense, a simulation generated by our brains, designed to provide useful information about our environment without necessarily being a literal representation of what is actually there. This observation has been used by some philosophers to argue that the question of whether we are in a simulation is, in a certain sense, beside the point. We are already in a simulation generated by our own brains. The question of whether there is another, larger simulation containing this one is interesting, but in some ways secondary. What matters is the experience itself, the subjective texture of being conscious, regardless of what physical or computational processes underlie it. This is a thought-provoking perspective, but it does not fully dissolve the simulation question. The brain-generated simulation we experience has, on the conventional view, a physical reality behind it. The colors we see may be interpretations, but they correspond to real electromagnetic radiation interacting with real photoreceptors in real eyes. The sounds we hear may be interpretations, but they correspond to real pressure waves in real air. The simulation our brains generate is a model of an external reality, and the existence of that external reality is what the simulation hypothesis calls into question. If the external reality is itself a simulation, then our brain-generated experience is a simulation of a simulation, doubly removed from any underlying physical truth. The consciousness question, then, takes on multiple layers in the context of the simulation hypothesis. There is the question of what consciousness itself is, how it arises, and whether it can exist in computational systems. There is the question of how the brain-generated experience relates to the underlying physical or computational reality. And there is the question of how all of this relates to the possibility that the entire universe is itself a computational construct. These questions are entangled with each other, and addressing any one of them requires taking positions on the others. What is striking about consciousness from the perspective of the simulation hypothesis is how central it is to the entire question. The simulation hypothesis is interesting only if there are conscious beings within the simulation. A universe being computed with no one inside to experience it would not be interesting in the same way. It would be merely a complex pattern of bits, no more meaningful than any other pattern. What makes the simulation hypothesis significant is the suggestion that conscious beings, beings with inner lives and genuine experiences, might exist within a computed reality. And this suggestion forces us to confront the deepest mystery of mind, the question of how subjective experience can arise from anything at all, computational or otherwise. The hard problem of consciousness, in the context of the simulation hypothesis, becomes a question about the nature of the computation. If consciousness is a feature of certain kinds of computation, then we must ask what makes those kinds different from other kinds. If consciousness is not a feature of computation at all, then we must ask what it is a feature of, and how it could exist in a universe that, on the simulation hypothesis, is fundamentally computational. Neither of these questions has a clear answer, and the answers we give will determine in large part our overall view of what kind of universe we inhabit. The simulation hypothesis does not solve the problem of consciousness. It deepens it by tying it to the deepest question of all, the question of what reality itself ultimately is. The hard problem of consciousness intersects with the simulation hypothesis at one of the strangest features of the physical universe, a feature so peculiar that physicists have spent nearly a century trying to make sense of it. That feature is the role of observation in determining physical outcomes. According to the standard interpretation of quantum mechanics, the act of observing a physical system fundamentally changes the system. Particles that exist in superposition in multiple states simultaneously collapse into a single definite state when they are observed. The wave function, which describes all the possible outcomes of a measurement, becomes a single actual outcome at the moment of observation. Before observation, the system is in a state of probabilistic indeterminacy. After observation, it is in a state of definite reality. Something about the act of observation itself seems to crystallize the universe into a particular configuration. This observer effect, as it is sometimes called, has been verified experimentally in countless ways over the past century. The famous double-slit experiment mentioned earlier is one example. Particles passing through two slits behave as waves, producing an interference pattern when they are not observed. They behave as particles, producing two simple bands when they are observed. The mere presence of an observation apparatus, regardless of whether anyone is actually looking at the results, changes the behavior of the particles. The observer effect is real, reproducible, and well documented. What it actually means, however, is one of the most contested questions in physics. There are several major interpretations of quantum mechanics, each of which gives a different account of what observation actually does. The Copenhagen interpretation, the oldest and still most widely taught, holds that the wave function literally collapses at the moment of measurement, transitioning from a description of possibilities to a description of actualities. The many worlds interpretation, proposed by Hugh Everett, holds that the wave function never collapses. Instead, every possible outcome of every measurement actually occurs, with reality splitting into multiple branches at every quantum event. The pilot wave interpretation, originally proposed by Louis de Broglie and developed by David Bohm, holds that particles always have definite positions, but those positions are guided by an underlying wave function that we cannot directly observe. Each of these interpretations is mathematically equivalent in its predictions, but they paint dramatically different pictures of what is actually going on. From the perspective of the simulation hypothesis, the observer effect takes on a particular significance. It is exactly the kind of optimization that one would expect a sophisticated simulation to employ. A simulation that needed to track the precise state of every particle in the universe at every moment would be enormously wasteful. There is no reason to compute the detailed behavior of particles that are not interacting with anyone or anything that cares about them. Far better to track only the probability distributions, the ranges of possible behaviors, and to commit to specific values only when those values are actually needed for some downstream computation. The downstream computation, in this case, is the experience of conscious observers. When an observer measures a particle, the simulation must produce a definite result because the observer's experience depends on it. Until then, the simulation can save resources by leaving the particle in a superposition. This interpretation does not require any particular position on the deeper interpretive questions of quantum mechanics. The mathematics works the same way, regardless of how it is interpreted. But the structural similarity to computational optimization is striking, and it has led several physicists to suggest that the observer effect should be taken as evidence for the simulation hypothesis. The argument is not that the observer effect proves the simulation hypothesis. It is that the observer effect is exactly what the simulation hypothesis would predict, and that this fit is too good to ignore. There are reasons to be cautious about this argument. The observer effect, properly understood, does not actually require a conscious observer. It requires only an interaction with another physical system. The wave function of a particle collapses when the particle interacts with a measurement device, regardless of whether anyone is looking at the device. This is sometimes overlooked in popular accounts of quantum mechanics, which tend to emphasize the role of the observer in a way that suggests consciousness itself is involved. In strict interpretation, the role of the observer is much less metaphysical. Any sufficiently irreversible interaction with the environment will cause wave function collapse, including interactions that have nothing to do with consciousness. Still, the question of what counts as an interaction and why some interactions cause collapse while others do not remains poorly understood. Some physicists, including the late Eugene Wigner, have argued that consciousness does play a special role in quantum mechanics, that the chain of interactions that leads from particle to measurement device to recorded result must eventually terminate in a conscious observer for the wave function to truly collapse. This view is not the mainstream position, but it has been defended by serious thinkers, and it remains a live possibility within the interpretive debates over quantum mechanics. From the perspective of the simulation hypothesis, this view would suggest that consciousness is not just incidental to the simulation, but central to it. The simulation renders definite reality only when consciousness requires it, and consciousness becomes the engine that drives the universe from possibility to actuality. There is another aspect of the observer effect that bears on the simulation hypothesis, and it has to do with the delayed choice experiment. This is a variation on the double-slit experiment, originally proposed by John Wheeler and later performed in various forms. In the delayed choice experiment, the decision about whether to observe which slit a particle goes through is made after the particle has already passed through the slits. Astonishingly, the particle's behavior, whether it acts as a wave or as a particle, depends on the choice made after the fact. If the experimenter decides to observe which slit the particle went through, the particle behaves as if it had gone through one slit. If the experimenter decides not to observe, the particle behaves as if it had gone through both slits. The decision, made after the fact, seems to retroactively determine what the particle did. This is a profoundly counterintuitive result, and it has been verified experimentally many times. From a classical perspective, it seems to violate causality, suggesting that future events can influence past events. From a quantum perspective, it can be made consistent with the standard formalism, but only by accepting that the particle's behavior was never really determined until the observation was made. The particle did not have a definite path through the slits. It had only a probability distribution of paths, and the path it actually took was determined retroactively by the choice to observe or not. From the perspective of the simulation hypothesis, the delayed choice experiment is consistent with a particular kind of computational architecture. It is consistent with a simulation that does not commit to specific values until those values are actually needed for some computation involving conscious observers. The simulation does not need to decide what path the particle took until it needs to produce a result that depends on that path. When the experimenter decides to observe, the simulation must produce a definite path. When the experimenter decides not to observe, the simulation can produce a result consistent with the particle having taken multiple paths simultaneously. The decision about which mode to use is made, in effect, when the observation is made, regardless of when the underlying physical events occurred. The simulation operates lazily, computing only what is needed and only when it is needed. This lazy evaluation, as computer scientists call it, is a well-known optimization technique. It is used in many programming languages and in many simulation environments. The idea is that a computation should not be performed until its result is actually needed, because performing computations that turn out to be unnecessary is a waste of resources. A simulation that uses lazy evaluation can defer the resolution of physical states until those states are actually queried, potentially saving enormous amounts of computational effort. The fact that the universe seems to behave in this way, with observation playing the role of the query that triggers resolution, is suggestive of exactly this kind of architecture. Whether the observer effect actually reflects a computational architecture, or whether it is a feature of physical reality that has no deeper explanation, is a question that current science cannot answer. But the structural similarity between quantum measurement and computational optimization is real, and it is striking. The universe behaves in many respects like a simulation that conserves resources by deferring computation until necessary. Whether this behavior reflects the underlying nature of reality, or whether it is a coincidence that arises from the deeper structure of physical law, depends on how seriously we take the simulation hypothesis as a description of what the universe actually is. What is clear is that the relationship between observation and physical reality is far more intimate than classical physics would suggest. The universe is not a passive backdrop against which observers move. It is a dynamic system whose behavior depends, in subtle but real ways, on the act of observation itself. Whether this dependence reflects a computational architecture, a feature of consciousness, or some deeper aspect of physical law is a question that remains open. But the observation effect, in all its strange and counterintuitive forms, is one of the most suggestive pieces of evidence in the entire case for the simulation hypothesis. It is exactly the kind of thing one would expect to find if reality were being computed. And the more closely we examine it, the stranger it becomes. The strangeness of quantum observation pales next to another feature of the universe that has puzzled cosmologists and physicists for decades. It is the precise tuning of the fundamental constants of nature, the numerical values that determine how strong gravity is, how massive electrons are, how tightly atomic nuclei hold themselves together, and how the universe has expanded over time. These constants, taken together, form the parameters of physical reality. They are the dials and switches that determine what kind of universe we live in. And when physicists examine these constants closely, they find something remarkable. The values appear to be calibrated with extraordinary precision to allow the existence of complex structures, including stars, planets, chemistry, and life. This observation, sometimes called the fine-tuning problem, has been one of the deepest puzzles in cosmology for over half a century. The fundamental constants of nature could, in principle, take any values. The strength of gravity could be slightly stronger or slightly weaker. The mass of the electron could be slightly different. The cosmological constant, which determines the rate at which the universe expands, could have any value across many orders of magnitude. There is nothing in current physics that requires any of these constants to take the specific values they have. They are, as far as we can tell, arbitrary parameters. Yet when we examine the consequences of changing these values, even slightly, we find that the universe becomes radically inhospitable to anything resembling complex structure. Consider some examples. If the strength of the strong nuclear force, which holds atomic nuclei together, were just a few percent stronger, all the hydrogen in the early universe would have fused into helium, leaving no hydrogen for the formation of stars or for the chemistry of water. If the strong nuclear force were just a few percent weaker, atomic nuclei beyond hydrogen would not be stable, leaving the universe with only hydrogen and no heavier elements. Either way, no chemistry, no stars, no planets, no life. The actual strength of the strong nuclear force is precisely tuned to allow nuclei to form, but not so tightly that all hydrogen is consumed. The window of viable values is remarkably narrow, perhaps a few percent on either side of the actual value. Similar fine-tuning is observed across other fundamental parameters. The ratio of electromagnetic force to gravitational force determines the relative sizes of atoms and stars. If this ratio were slightly different, stars would either burn out too quickly to support stable planetary systems or never ignite at all. The mass of the neutron is just slightly greater than the mass of the proton by a tiny but crucial amount. If neutrons were lighter than protons, all protons would decay into neutrons, and there would be no atomic structure as we know it. If neutrons were significantly heavier than protons, all neutrons would decay rapidly, leaving only hydrogen with no possibility of more complex chemistry. The actual ratio is exactly what is needed to allow nuclei to form and remain stable. The cosmological constant, the parameter that determines how rapidly empty space expands, is perhaps the most striking case of fine-tuning. The observed value of the cosmological constant is approximately 10 to the negative 120 in natural units. This is the smallest non-zero number that appears anywhere in fundamental physics, and it requires explanation. Theoretical estimates of what the cosmological constant should be, based on quantum field theory, give values that are around 120 orders of magnitude larger than the observed value. The discrepancy between the theoretical expectation and the actual value is sometimes called the worst prediction in physics. If the cosmological constant were closer to its theoretical value, the universe would have expanded so rapidly after the Big Bang that no structures could have formed. The observed value, while extremely small, is consistent with a universe that allows galaxies, stars, and planets to form. It is fine-tuned to an almost incomprehensible degree, with the observed value differing from any randomly chosen value by something like a factor of 10 to the 120. These fine-tunings have prompted serious scientific and philosophical debate. The conventional explanation, called the anthropic principle, holds that we should not be surprised to find ourselves in a universe whose parameters allow for our existence, Because in any universe whose parameters did not allow for our existence, there would be no one to make the observation. We are biased observers, constrained to find ourselves in universes that can support observers. This explanation is logically valid, but it is not entirely satisfying on its own. To make it work, we typically need to assume that there are many universes, each with different values of the fundamental constants, and that we just happen to be in one of the rare universes where the values are favorable. The multiverse hypothesis in various forms provides this kind of explanation, but it has its own difficulties. It is not directly testable, and it requires postulating the existence of an enormous number of universes that we can never observe. From the perspective of the simulation hypothesis, the fine-tuning problem takes on a different complexion. If the universe is a simulation, then the fundamental constants are simply parameters of the simulation, set by whoever or whatever designed it. The fact that the parameters are tuned to allow complex structure is not a mystery. It is a design choice. The simulators, whoever they are, chose values that would produce a universe with stars, planets, and life, presumably because such universes are more interesting to simulate than universes without them. The fine-tuning problem becomes a fine-tuning solution, providing direct evidence that the universe was, in some sense, designed. This argument is suggestive, but it should be approached with care. The leap from fine-tuning to design is one that has been made many times in the history of human thought, often in service of theological arguments. The simulation hypothesis offers a secular version of the same argument, replacing a divine designer with a sufficiently advanced civilization. Whether this version of the argument is more compelling than the theological version depends on which assumptions one is willing to make. Both versions face the same fundamental problem that the inference from apparent design to actual design is logically valid but not necessarily compelling. Apparent design can arise from non-designed processes such as natural selection or anthropic selection, and we have no way of distinguishing between actual and apparent design from inside the system. Still, the fine-tuning of the fundamental constants is one of the most striking features of the observable universe, and any complete account of why we exist must address it. The simulation hypothesis offers one possible account, the multiverse hypothesis offers another, and various theological views offer others. None of these accounts has gained the status of established science, and the question remains genuinely open. What can be said is that the fine-tuning is real, that it is far too precise to be the result of chance unless there are many universes from which to select, and that any account of physical reality must accommodate it in some way. There is another aspect of the fine-tuning problem that bears specifically on the simulation hypothesis. If the universe is a simulation, then we might expect the parameters to have certain features that would be characteristic of a design system. We might expect them to be expressible in simple mathematical terms, to relate to each other in elegant ways, and to be precisely the values that produce a universe of the desired type, with no wasted precision and no unnecessary complexity. When we examine the fundamental constants, we find that they do exhibit some of these features. They can be expressed in simple ratios, and the ratios are often related to each other through elegant mathematical relationships. Many of the constants are dimensionless, meaning they do not depend on any particular system of units. They are pure numbers, characterizing the structure of physical law in absolute terms. The fine structure constant, for example, is a dimensionless quantity that characterizes the strength of electromagnetic interactions. Its value is approximately 1/137.036. Why this value, no one knows. It cannot be derived from any deeper theory. It must be measured experimentally and inserted into the equations of physics by hand. The same is true of many other fundamental constants. They are arbitrary, in the sense that they are not predicted by any theory we have. They are also remarkably specific, taking values that allow the universe to function as it does. From the perspective of the simulation hypothesis, this is exactly what we would expect. The constants are parameters of the simulation, set by the designers to produce a particular kind of universe. They are not derived from any deeper logic. They are simply chosen, like the settings of a complicated video game. This perspective, while speculative, offers a way of making sense of one of the deepest puzzles in physics. It does not prove the simulation hypothesis, but it shows that the hypothesis has explanatory power. It accounts for features of the universe that other approaches struggle to explain, and it does so in a way that is internally consistent and that does not require any obvious leaps of faith. The simulation hypothesis is not a complete theory of physical reality, but it is a serious candidate for understanding why the universe is the way it is, and the fine-tuning of the fundamental constants is one of the most compelling pieces of evidence in its favor. Yet this evidence raises new scientific questions. If the constants of nature are parameters set by some external system, what determines the values of those parameters? Are there constraints on what values are possible, or could the parameters take any values whatsoever? These questions point toward an even deeper foundation of physical reality, one that has emerged from theoretical physics in recent decades and that suggests something even stranger about the nature of the universe. It suggests that, at the deepest level, reality is not made of matter or energy at all, but of information.